So it's my pleasure to welcome Yoshito Hirata, who will be talking about unified time series analysis for nonlinear deterministic and stochastic systems.
Thank you very much. Thank Boumediene for giving me a chance to talk in this seminar. And today I will discuss, discuss that we can use some technique of nonlinear time series analysis for nonlinear deterministic system can be also used for nonlinear stochastic systems as well. Roughly speaking, we can divide the dynamic system into the 4 categories depending on the 2 axes. The one of the axes is whether the underlying dynamics is deterministic or stochastic. The other axis is whether the underlying dynamics is linear or nonlinear. We say that underlying dynamics is deterministic if the future state can be described by the function of the current state and the past state without the probability components. Otherwise, it's stochastic. We say the underlying dynamics is linear if the function is a summation of the current state and the past states. Otherwise, the dynamics is nonlinear. And also for time series analysis, there are some assumptions for the analysis. For example, if we consider the autoregressive linear model, we eventually assume that the underlying dynamics is linear and stochastic. Therefore, if we would like to consider nonlinearity, we have to include the nonlinear terms into the model. Otherwise, we get a long answer. We may get a long answer. Therefore, we would like to discuss today that the assumption, so how to test the assumptions of these 4 categories, especially for the nonlinear stochastic systems. So the past 4 decades, the nonlinear time series analysis has been developed, but the assumption is a nonlinear deterministic. Therefore, if we apply this, such kind of time series analysis for the nonlinear stochastic system, we may get a long answer. But today, we'd like to discuss here that some particular type of analysis, such as a permutation and recurrence plot, can be also used, which are mainly used for the nonlinear deterministic system until now, but can be used for the nonlinear stochastic system. This is a point that I would like to make today. Firstly, before starting the main part of the talk, I would like to define what a nonlinear stochastic system I would like to consider here. X of t is a current state. S of t is a current probability component. And x of t plus 1 is a future state. Therefore, the future state is a function of the current state and the current probability component. We assume that the function f is continuous in terms of x of t and s of t. And if we fix x of t, x of t plus 1 and s of t is 1 to 1. Therefore, they are embedding. So this is a system we would like to consider for the nonlinear stochastic systems. So to judge to classify the system into the 4 categories shown in the sphere, first we would like to discuss this axis, linear nonlinear axis. The key point is, as I'll discuss later, that the 30 years ago, the surrogate data analysis has been proposed, but so the assumption is that the underlying dynamics is linear stochastic. To identify the nonlinearity, people often use the statistics which characterize the deterministic and stochastic axis. Therefore, this last 3 decades, this linear linear nonlinear axis and the deterministic stochastic axis have been mixed up. That's the reason why that we could not identify the nonlinear stochastic system. But to identify nonlinear stochastic system, what we do is to prepare the two independent hypothesis tests. One is for the linear nonlinear axis. The other is the determinism stochastic axis. I would like to start for the axis of the linear nonlinear axis first. So the surrogate data which has developed the last 3 decades is the main player is iterative amplitude adjusted Fourier transform surrogate, which preserves the power spectrum almost perfectly, and the distribution of the spatial distribution of the points perfectly. Therefore, the underlying new hypothesis is the time series generated from the monotonic nonlinear transformation of linear noise. The left-hand side, we show the original time series, and right-hand side shows the surrogate data. Therefore, it is so the left bottom panel, we show the power spectrum. These power spectrum matches very much. And the spatial distribution is matched as shown in the right bottom panel. So we generated many surrogate data, and we look for the difference between the original data and the surrogate data using a test statistics. And the key point is how to choose the test statistics. So in the existing literature, many people use test statistics based on the determinism, such as the prediction errors. But here, I would like to propose to use just a temporal mean of x of t squared times x of t plus 1 squared as a test statistics. Because this statistics doesn't have any relation with determinism, so we can make the axis of linear nonlinear axis free from the axis of determinism and stochasticity. This is how we can separate these two axes for establishing the test for linearity. Right-hand side shows the result of the test. So I think that we generated some, I think around 40 surrogate data and obtained the distribution of this test statistics for the autologous linear model and fractal Gaussian model, Gaussian noise. The value obtained from the original data shown by the red vertical axis is within the minimum and the maximum of the test statistics obtained from the surrogate data. So that we cannot reject the new hypothesis that the underlying time series is generated from the nonlinear transformation of the linear noise. But in case of logistic map, Garch model, noise induced order, and Bernoulli shift, the original value obtained from the red vertical shown by the red vertical axis is out of the interval specified the minimum and the maximum of the surrogate data. Therefore, we can reject the new hypothesis. Therefore, we can infer the nonlinearity for the underlying dynamics. This is the story for the test for the linearity and nonlinearity. So we would like to get into the more difficult question. I mean, for the test for the stochasticity and determinism. To do that, first we would like to discuss about the partition. Partition divides phase space into the some region number s of regions disjointly. Therefore, we consider the substring so that if we observe a system with a partition, for each time we obtain the symbol related to each subregion of the partition. Therefore, if you observe n times for the system, the complexity we can represent is s to the power n. S is now the number of the subregions. Therefore, the complexity is exponential. But stochastic system may produce the infinite amount of information per unit time. That's why that approach of the partition cannot fully characterize the stochastic system. So this is why that it is known that there is no generating partition for the dynamic for under the existence of dynamical noise. So how can characterize such kind of system? This is a point I would like to make. The simple answer for this question is we would like to make the representation more complex. I mean, it's a super exponential complexity. We use the super exponential complexity to represent the underlying dynamics for the for describing the stochastic system, which is we would like to do. For the first approach I used was a permutation. It is also called ordinary patterns. This is the inequality relations among the consecutive measurements. So if the length is 3, there are 6 possibilities. Third, second, first, third, first, second, second, third, first, second, first, third, first, third, second, and first, second, third. So if the length becomes 4, there are 24 possibilities. If the length becomes 5, there are 120 possibilities. If the length becomes 6, there are 720 possibilities. Therefore, the complexity grows as a n factorial. This complexity is super exponential. This super exponential growth is the reason why that we can use permutation to estimate the topological entropy or metric entropy without using generating partition. So that we allow some redundancies to represent the time series. This is a key point of the permutation. We look into the detail how these redundancies work for permutation for stochastic system. For the deterministic system, it is known that there is a theorem by Amigo and Kendall, 2007, which says that the number of appearing ordinary pattern increasing exponentially for expansive deterministic dynamical system when the length of ordinary patterns is prolonged. So therefore, for deterministic expansive system, there are some ordinary patterns which doesn't appear. It is possible for representation, but it doesn't appear in the time series. These not appearing ordinary patterns is called forbidden patterns. Therefore, the Professor Amigo and his colleague use this forbidden pattern as a signature of the deterministic system. So we like to use this theorem, but more rigorously. So we take the contraposition of the theorem, which says that if the number of appearing ordinary pattern does not increase exponentially, the underlying dynamic is either stochastic or non-expansive. Here, expansive means that the distance between 2 points will be separated but more than a certain distance if we iterate these 2 points. Therefore, we can check this expansiveness by looking at the recurrence plot I will introduce later. Therefore, we can check the expansiveness easily. Therefore, if we show that the underlying dynamics is expansive and has a non-exponential growth, then the only possibility is stochasticity. This is a logic we would like to use. So to test the non-exponential, test the property of non-exponential growth, from the time series, we would like to fit the logarithm of the number of appearing ordinal patterns with a linear model. Then if the linear model fits well, the growth of appearing ordinal pattern is exponential. For comparison, we also fit the quadratic model for the logarithm of the appearing ordinal patterns. And we compared these two models, which model is better, by using the F distribution with appropriate degree of freedom. Therefore, the underlying null hypothesis is a number of appearing ordinal pattern increases exponentially. Therefore, that's a trick that we can set stochastic system as an alternative hypothesis. The following are the examples. I use the length of time series is set to the 1 million, if I not mention it. This is a speed of the growth speed of the appearing ordinal patterns of various models. For logistic map and Bernoulli shift, the number of appearing ordinal patterns increases exponentially because now the vertical axis is normalized as a logarithm of the number of appearing ordinal patterns. For noise-induced order, number of appearing ordinal pattern increases sub-exponentially. For other stochastic model like autoregressive model and the fractal Gaussian noise, number of appearing ordinal patterns grows super exponentially. So we test this growth, test the speed of growth of the variety of the appearing ordinal patterns using the F distribution I discussed in the previous slide. In this way, that now we can in the 2 years ago I could apply the test for the identifying the stochasticity explicitly, but the problem was that now the length of time series should be the 1 million or longer. It is too long practically. To overcome this problem, I first get into why that the permutation or ordinal pattern can be used for characterizing stochastic system. So eventually the permutation can characterize nonlinear stochastic system. That's because the permutation can establish one-to-one correspondence between the joint set of state and input series in the limit of the size of permutation going to the infinity. There's a statement of the theorem we published a year ago. So eventually that if we specify permutation, we can now narrow down the possibility of state. Therefore, we can estimate the state corresponding to the time interval of the permutation. Now the length of the permutation is 8. Therefore, this is the edge of the permutation, and this is here is another edge of the permutation. Therefore, the time interval corresponding to the permutation, so we can estimate the state value of state better than just using the simple mean as a estimate shown by the red dotted line, red dashed line. And if the time becomes positive, it becomes a time series forecast as well. But for noisy logistic map and the noisy Henon map, we can also estimate the state better than just using the simple mean. that means that it becomes a better for time series forecast as well. Because of this one-to-one correspondence, we can also specify the input series. That means the stochastic input. This is shown in the lower panels. For noisy logistic map, red dashed line that shows the case that we set the mean value of dynamic noise as a estimate, and red blue line shows the error bars for estimating the dynamic noise, value of dynamic noise for corresponding time, relative time. So the gain is a little bit small because we use a finite length of the permutation, but we can achieve the better estimate for dynamic noise compared to the just using the mean value of the dynamic noise, because so even though that there is no correlation in terms of the input of the dynamic noise. So therefore like a sphere shown in the right hand side, we can estimate the state as well as the stochastic input when we specify the permutation. That's because that if we consider infinite length of the permutation, we can eventually establish one-to-one correspondence between the permutation and the joint set of state and input. This one-to-one property is a reason why that the permutation can be used for characterizing stochastic system. Now I got the hint. And also now in this slide, we assume that we have a time series of dynamic noise for the past part of the time series. But even if we don't have a past part of time series for dynamic noise, we even can estimate the dynamic noise if there are many systems which are subject to the same common dynamic noise. To do that, we need recurrence plot, but I will introduce later. Therefore, if you're interested in, please look at the detail. We find the details in this paper. Therefore, now we know the reason why that permutation can identify the characterized stochastic system. This is the one-to-one property between the permutation and the joint set of the state and the input series. But the problem with permutation is that we need a long time series, 1 million or longer. To shorten the time series which is necessary, I try to replace the permutation with a recurrence plot. Recurrence plot was originally proposed for visualizing time series data. Both axes correspond to the same time axis. For pair of time, we calculate the distance, and distance is smaller than threshold, epsilon. Then we plot a point at the corresponding place. Otherwise, we do not point there. This simple graph can show a lot of things. For example, periodic time series, we can have a recurrence plot with the periodic patterns shown up on the right-hand side. I'll show the other examples. For the white noise, we can have points which are plotted randomly on the recurrence plot. For deterministic chaos, in this case, is a logistic map. We can see the many diagonal line segments. Therefore, by looking at the recurrence plot, we can learn a lot of things about the underlying dynamics, especially the diagonal lines characterize the determinism. Therefore, the portion of the points forming the diagonal line is used for the index of determinism. So this is a research intensively done and from the 1990s to the 2010 or something like that. And for the, I laid these three recent review papers for the review article for the recurrence plot. For from the recurrence plot, we can learn a lot of things. But from the definition, we can see that the recurrence plot convert continuous information of the original time series into a binary information or zero one matrix. Therefore, we may think that by when we convert the time series to a recurrence plot, we may lose a lot of information. But actually, from the recurrence plot, we can reproduce rough shape of original time series. This is a recipe for how we can reproduce original time series from a recurrence plot. This time series is the original time series that we have. From this time series, we obtain the recurrence plot shown on the right-hand side. First things we do is construct a graph from this based on this recurrence plot. In this graph, each node corresponds to each time index. And each point, each symmetric point corresponds to each edge. And the GI corresponds to the set of time indexes plotted to the ith column. Therefore, if G3, it is G3, it is a set of 3, 4, 5, 6. And for each edge, we assign the cost which associated with this W shown in this equation. Second term on the right-hand side is a good measure for defining the closeness of the two time point in the original time space, original phase space, and the denominator. At the denominator, we consider the union of two columns. For numerator, we consider the intersection of two columns. Therefore, by using this W, we can approximate the local distance between the ith point and the jth point if these points are the neighbor. Because we can reconstruct a good local metric, we connect these local metric to reconstruct the global distance. This is the second step. We calculate the shortest distance between every pair of the nodes and obtain the distance matrix. Then we eventually obtain the geodesic distance in the original phase space. Therefore, we apply the multi-dimensional scaling so that we can find the points which preserves the distances between every point of the pairs. So if we look at the largest eigenvalue on component, this time series looks similar to the original time series. Good things of this algorithm, it works even if the original time series is a high dimensional, or even though I showed the one-dimensional example. And another good reason for this conversion is there is two papers showing that although it's a toy model, but there are two proofs that which show that this algorithm works well. Another good reason for this theorem is we don't assume anything on the time series for the underlying dynamics. Therefore, the time series may be generated from the nonlinear stochastic system. This is the starting point. I began the research on the theory of the nonlinear stochastic system on a recurrence plot. And I focus on the triangle part of recurrence plot shown in this diagram, the gray shaded area. So the complexity of this red gray shade pattern of the red, gray shaded area is 2 to the n times n minus 1 over 2. The complexity is super exponential. It's similar to the permutation. But good things on the recurrence plot is if the time series length is large n, then we can obtain the almost over order n squared recurrence triangles. We especially say that if the recurrence plotting touching to the central diagonal line, we call them central recurrence triangles. So the number of the recurrence triangle is order n squared if the length of time series is n. So eventually I was inspired by the research of the Corso et al. They consider the recurrence microstate. It is a squared region of the recurrence triangle. But I decided to cut down the lower right part of the recurrence triangle because if the recurrence plot is symmetric in terms of the central diagonal line, and also if we cut down the right bottom part of the recurrence triangle, we can consider the larger motif. That's the reason why we consider the gray shaded area like a recurrence triangle. And also if we consider the central recurrence triangle, we can show that similarly to the permutation, that we can show the one-to-one property for a recurrence triangle with a joint set of state and input series. So that if the underlying dynamics is expansive, topological transitive, and non-symmetric, then that if we specify the central recurrence triangle, we can identify the state and input series with the degree of freedom of the symmetry. So this is one-to-one property is a nice property, and it is a basis for the constructing the theory for nonlinear stochastic system. And therefore, based on this theorem, I obtained a similar result as a permutation, which says the variety of appearing recurrence triangle increases exponentially as their size increased if the underlying dynamics is deterministic, expansive, and topological transitive. Here, topological transitive means that if there is an open set, if we return there is a point which return to this open set, which come to the open set eventually. Therefore, we have a theorem as well. Therefore, we also see the numerical results. I show that tendency of the growth speed of the appearing recurrence triangles, but this result looks similar to the previous one in the permutation, but the difference is time series is a length. Now the length of time series is 10,000. So for the length of time series is quite shorter than the case of the permutation. But case of the deterministic system like a logistic map, tent map, antisymmetric cubic map, NO map, and Ikeda map, the number of appearing ordinary patterns tend to increase exponentially. For the model of noise-induced order, it's very hard to see from the figure, but most of the major time series has a sub-exponential growth of the permutation. The variety of recurrence triangles. For the case of the white noise and autoregressive linear, first order autoregressive linear model and the Gauch model, the variety of the appearing recurrence triangles tend to grow super exponentially. So this is a result of time series generated from the 10,000. Therefore, it is practical. So therefore, I finally applied the engine data analyzed by the Ken and Boo 2003. There is a two types of engine data. The one is specified by the parameter P30. The other one is a parameter 75. For the parameter 30, we can see the super exponential growth as shown by the red solid line. And that means that it can be related to the stochasticity for the underlying dynamics. But in case of the engine of the parameter 75, we cannot deny the exponential growth for the based on the appearing recurrence triangles. So depending on the parameters, the engine's behavior can be different. Therefore, this is almost the end of my talk. That today I discussed that the permutation, the recurrence triangles can establish one-to-one property, which is a basic property for establishing the theory for characterizing nonlinear stochastic system. So therefore, if the size of motif becomes infinite, we can establish almost one-to-one correspondence between each motif and a joint set of state and the input series. Therefore, you can eventually establish the symbolic dynamics, which is almost equivalent to the original stochastic system. Key idea is a super exponential growth. That means the combinatorial complexity. In case of permutation, it is a factorial order. In case of recurrence triangle, its growth speed is faster than the factorial order because it is due to the power of the n times n minus 1 over 2. And yeah, therefore and we can use a recurrence plot for the shorter time series than the permutation because in case of recurrence triangle, we can have order n squared recurrence triangle if the length of time series is n. But in case of the permutation, we just have order n permutations. So that's the reason why that the recurrence plot we can use shorter time series to characterize the stochastic aspect of the underlying dynamics. Yeah, this is almost the end of my talk. Therefore, now that I would like to the take-home message is we can use permutation and recurrence plot for characterizing deterministic and stochastic nonlinear systems, both. This is the message. Thank you very much.
Thank you very much. Any questions? So for the noise here, it doesn't. Yeah, just maybe I can ask a question. So the nature of the noise here it doesn't matter. It can be Brownian motion. It can be bounded, unbounded, fractional Brownian motion. It can be anything. Or is there an impact on the nature of the noise here?
Therefore, the assumption of the noise is constrained by this formula.
Yeah.
Therefore, if we fix x of t, the noisy component and the future state becomes 1-to-1.
So anything else is noise. So for you, like noise is just anything. So it's
Therefore,
we're not putting any mathematical assumptions on the noise, right?
If, for example, to consider the simpler case, we consider the map on the interval, and in this case, that x is within the interval. To define x to be the x in the interval, s of t also becomes the interval within the interval. Therefore, that means that the noise should be bounded, I think. But if you apply some fancy transformation, and you may consider unbounded noise, but it's natural to consider the bounded noise, I think.
Okay, so for you, like in a way, the choice by default for the noise is a bounded one. Yeah. For example, in OU, if you just like take a simple OU process, actually at least here it's discretized, but if you do like an OU process, so it's so it's a Brownian motion. So you would transform the noise to make it bounded, and then you apply your approach, or how would you approach?
I didn't consider that case seriously yet, but according to the definition of this nonlinear stochastic system, so we somehow treat stochasticity of the OU process or Brownian motion into the bounded noise. So we need some transformation, but there is no such transformation. But therefore, in that case, in that sense, that our result might be limited. But I'm not sure.
But in any case, maybe like observable noise in nature is somehow bounded by default. I don't know. Yeah.
Therefore, if you consider the Gaussian noise, for example, it's unbounded. Therefore, in the case that x also become unbounded, but because I use a topological transitivity or such kind of things, therefore our theoretical result doesn't go well with the unbounded case, I think.
Okay. Yeah. So in a way, I mean, the model of noise you are choosing is the bounded one, and then the exceptional cases are the ones which are unbounded. I mean, it's not like the other way around, where people consider unbounded noise as the default, and then bounded noise becomes an exception. So here you are in a way considering the other way around for the models of the noise. Yeah. Yeah. Okay. All right. Yeah.
So if we interpret this first definition of the nonlinear stochastic states naturally, we consider the bounded noise, I think.
Yeah. Okay. Yeah. So yeah. This is what I understood. Okay. Thank you. Yeah. Other questions? Maybe another question. Did you apply like to some like practical examples, like in seizure detection? For example, where you have like a lot of like noise, like neurological signals, where you have a lot of noise, right? I mean, in the like if from EEG signal, where you want to detect or predict seizures. So there's, I mean, the signals are very noisy, but you could see that there is some patterns where you could eventually isolate a deterministic part from the noisy part, and the noisy part can come from the device, but they can come also from biological considerations, like in the brain signals. I mean, did you try to apply this kind of things to this neuro models from EEG measurements or these kind of things?
Yeah, I think that I have experience applying our method to the EEG data, and but I think that the analysis I proposed today could be used for the identifying the making the assumption clear. Because there's as I shown in the beginning of this talk that there are 4 categories in the dynamic systems. So therefore, we are applying the 2 independent tests of one axis. The one test is either linear or nonlinear. The other test is a deterministic stochastic. I mean, by specifying these properties, we can allocate the underlying dynamics into the one of the 4 categories in this slide. And based on the categories, so we can choose time series analysis we should use. Therefore, making the assumptions clear based on the proposed methods, we can have more appropriate answers for each question or each analysis of the time series analysis. Therefore, I say that the approach that I proposed today is very fundamental. Therefore, it's so based on this idea analysis that we can specify the assumptions we should make. Then we choose the appropriate time series analysis, because there are many time series analysis. I mean, even I think that there are time series analysis for the nonlinear stochastic system, even without even though that these assumptions have not been checked yet, but there are time series analysis for the nonlinear stochastic system. There are time series analysis for the nonlinear dynamic system as well. Therefore, my idea is first we specify the assumptions by the proposed test, then apply the time series analysis for each appropriate category. This is how we should use the test I propose.
Yes. Yeah, that's nice. I think I see potential here, especially as I told you in the context of EEG data, where it's not clear if the model should be viewed as deterministic or purely random, or yeah. Anyway, thanks again. Other questions? Yes, I'm the only one asking questions. Yeah, okay. Yeah, thanks a lot again for the very interesting talk, and then looking forward to future discussions with you. Yeah, all right. Thank you very much.
Thank you very much.
Thank you.
If there's shy people, please send me email. I mean, I would like to answer the question. Maybe there were some very unclear points that I during my talk. Therefore, please, if there are some questions, please feel free to send the email to ask me questions. Yeah.
Yoshito was CC'd in the seminar announcement, so his email is in the CC field. Yeah.
And also these papers are also most of the papers are freely available on the internet. Therefore, you can read the papers.
Yeah. Okay.
For the PRE paper, I think.
So the starting one would be the PRE paper, is the first paper to start with.
Yeah, this is under subscription, but other papers are published on the open access. Therefore,
But if you want to start with to understand your method, I mean, the starting point would be that PRE paper. Yeah.
I think this PRE paper is a good starting point, I think.
Yeah. Okay. Okay. Thank you very much.
Thank you.
Yeah. Thank you. Have a good day. Thanks. Take care. Bye bye. Thank you. Take care, everyone. Bye.